Hello everyone, this is video 1 about probability models in DNA sequence evolution. My name is Tagore Zhao and we will be going over the first chapter. Yay! And we'll be starting with section 1.2, and this video will cover page 5 to 7. I know it's very short, but we will be getting faster as we move forward. At the beginning of each chapter of this book, it will make a very interesting citation. I think it's very interesting, so I just listed it here. And you can see the first chapter is that all models are wrong, some are useful. And what does the first chapter talks about? What is the first chapter is about? It's about it introduces a bunch of basic models that are used in modeling the evolution of DNA sequence. Specifically in section 1, the title is Wright-Fisher Model, and then it goes to infinite aisles, and then infinite size, and then at the end it introduced the Monroe model. So what does that mean? When we're talking about modeling the evolution of DNA sequence, what kind of problems are we trying to study? Like what kind of information can we get from these models? There are two perspectives. One perspective is we are going forward. The kind of question looks like, if we're given an initial state, how does the gene evolve over generations? Will it come to an end, or does it keep moving forward? For example, if a single aisle is contained in the initial generation, what is its frequency in maybe the nth generation, or in the evolving progress? Does it change over time, or how does it change? This is kind of a forward perspective. The other is the backward perspective. If we're currently at the nth generation, if we're given a sample of aisles at the nth generation, what is the time of their most recent common ancestors? We will abbreviate it as MRCA in the later when we mention about most recent common ancestors. What is the time of their MRCA? Do they have the same? Do these sample of aisles have the same MRCA as the entire population, or what did already different? Like when are they different? And this is kind of a question that we work backwards. An analogy of this to perspective is like if you're looking at a parent, say like, oh, how's your kid? How's your grandson or granddaughter? It's kind of like forward. This is what it means by forward. If you're looking at a bunch of kids and say, hey, how's your parents? How's your grandpa or grandma? And so this is kind of like a backward direction of the problem. So. And I know this is kind of a high-level introduction of the perspectives, but U is pretty big and it's not very accurate. But you will be knowing about these things in great detail when we move forward. And the first model, and if you go to any probability or course in population genetics, the first model introduced is always the Wright-Fisher model. If you have a probability professor that works in application in biology, you probably have heard it before, or you probably have heard it in your basic probability course, and you might be even tested on these models. But now we will be introducing them like kind of a relative formal way. So what is the Wright-Fisher model? So we'll not talk about its biology counterparts, but talk about talk about the model itself. Okay. So consider a genetic locus. A genetic locus is you can think of as a container. It contains a bunch of diploid. And you can see that this black box is a genetic locus, and each generation we have, in this setting, we have like one genetic locus. We do look at what happens inside this genetic locus. And each genetic locus contains an individual diploid. And each diploid, you do not have to know what that is. It probably won't show up. This is the only time that will show up in this video. A diploid contains two aisles of types A, big A and small a. I will not use capital A because it's too hard for me to pronounce. So I will use big A and small a as a reference to these two aisles, the two type of aisles. So what does a diploid look like? Maybe it's a big A, big A, small a, and small a. There are three types of diploid when we are only having two types of aisles. The aisles actually, for example, in the famous Mandel's experiment, it's for the P's, they are maybe like wrinkled and round, right? This is a pretty famous like experiment and explanation of the owls. Okay, when we are looking at each genetic locus contains an individual diploid, and when we are using like each owl as a unit, it contains 2n number of owls. And for simplicity, we'll not be thinking about diploids in this time. We'll be thinking, okay, each genetic locus contains 2n aisles, and we will be talking about aisles as a unit of measure. So you can forget about the diploid. And then there are a few assumptions about Wright-Fisher model. First, that the generations is non-overlapping. By non-overlapping, we mean that, okay, the first generation, how do we produce the second generation? We randomly sample aisles from the first generation, and the sampled aisle produce a copy of itself, and then this copy of itself is being put into the second generation. So the first generation and the second generation, these two genetic locus, you can think of that as completely disjoint. There are no overlapping like aisles in between generations, and the sampling that we're experiencing is called random mating. This is also an assumption of the Wright-Fisher model, and there's no recombination, meaning that normally, like think about like mating, we will have you select a father and we'll select a mother, and their genes get recombined and it could produce the children, and there's no recombination. We select one parent in this setting, and this parent produces a copy of itself, and the copy is being put into the next generation. So there's no recombination. And another important assumption is that we assume that all the individuals have equal fitness. So what does it mean to have? What does the term fitness mean? Here is that it's a measure. It measures individuals, but it's not a mathematical measure. It measures individual ability to survive or produce offsprings. So this is only true if we have neutral evolution, meaning that the mutation does not change the fitness of the individuals. So, but you can just remember this kind of like identical assumption. Like these, although there are two types of aisles, but their fitness are the same. So, let's go over these assumptions like in the summary. Okay, what are all the assumptions? The first is that this is discrete, right? There's like generations are discrete, and the number of aisles, of course, they're not continuous. They're discrete, and they have non-overlapping generations. That means that each generation has its own genetic locus, has its own container containing all these aisles, and these aisles don't overlap. And constant population size. Oh yes, for each generation, it has a total number of 2n aisles in it. This is true for each generation. Equal fitness. Each individual has its the ability to produce or offsprings and survive is the same, and this is assumption under neutral evolution, meaning that the mutation does not change the fitness of the individual. And this random mating, meaning that we randomly select parents or from the previous generation. No recombination, meaning that we don't select this setting. We don't select like 2 or 3 or multiple. These maybe like you can select 2 diploids and they like select part of them and they recombine. No, we don't do that. We select each aisle and they just produce a copy of itself. There's no recombination, and we have finite number of aisles. This is very important. We will talk about infinite aisles model in the next section very quickly. So, okay, so you can see that if you're familiar with Wright-Fisher model, or if you're like familiar with Markov chain, you can clearly see that this can be formulated in the maybe let's say we have 2 types of aisles, right? Big A and small A, right? Let's let xn denote the number of A's, big A's, in the generation n. And we can clearly see this random variable xn is a discrete Markov chain. And I will not prove that. I think you can, if you're curious how it is proved, you can. I think it's very easy for you to check for yourself. Check the Markov property. And it is easy to see that since we are randomly sampling from a genetic locus. A genetic locus contains only two possibilities. You think about it, it contains two types of balls, right? You draw random drawing from these black box and these balls, and it's either black or it's either white, right? And does it sound familiar? It's a binomial distribution. If you know the previous generation, the number of big A's in generation n, then you will know the probability distribution of xn given xn minus 1. And it's a binomial distribution because each generation has 2n aisles, so the total we would make 2n draws. And what is the probability of success, or probability of drawing a big A? It depends on how many big A's are contained in the previous generation. So the number of big A's contained in the previous generation is given by, okay, xn minus 1 is the number of A's in the previous generation, in the generation n minus 1, over the total number of aisles in the previous generation is always 2n. So this is pretty easy. And okay, what is this Markov chain we talk about? This is discrete Markov chain. If we know its transitional probability, it is completely determined, right? A Markov chain, a finite discrete Markov chain it is completely determined by its transitional probability. Right? Since it's a binomial distribution, it's very easy, right? We can just write it down. If we are selecting, transitioning from I number of big A's in generation n minus 1 to j number of big A's in generation n, we are selecting j number of big A's from like a total population of 2n, with probably a success of pi to the j's power times 1 as pi to the 2n minus j power. Okay, and this pi is the probability of successfully selecting a big A from the previous generation, and we have gotten it here. It is pi is I over 2n. I here is the number of big A in the generation n minus 1. You can see it here. Okay, so then we have like build this model, and what is the expectation of x? What is the expectation of number of A's in generation n? So let's just write it down. Okay, it's actually pretty easy. It's xn, since we know that xn given xn minus 1 is a binomial distribution, so we can use this property, right? We use conditional expectation. It is equals to the expected value of expectation of xn given x minus 1, right? And you know what it is. You know what is the expectation of xn given xn minus 1? It's a binomial distribution, and it is 2n times xn minus 1. Right? This is n times pi, right? And we simplify it, right? It is equals to the expected value of x minus 1. And we can kind of do induction here, right? Like do induction backwards. It is accounting. Okay, it is eventually equals to the expectation at the initial distribution, right? Which is x0. Okay, this is actually a very interesting property. If you know martingale, this is actually a martingale with respect to itself. If you don't know martingale, it's perfectly fine. But I'm just mentioning here if it helps you to understand. And this kind of like it's called a martingale property. And we'll be using this property later when we are trying to prove fixation probability. Okay, another question will be what is the variance of xn? This is actually way harder to compute than the expectation. I will not go over this because I don't want to torture you guys with arithmetic. So I will just list it here, and the proof will be provided in the description, in the link in the description. Some guy actually write this proof in very nice LaTeX, so I will just attach in the description and without going over this tedious arithmetic. Okay. So, and for this lecture, we won't be we won't focus this on these variance things a lot. Okay, so a common questions will be, okay, we want to know, now we're looking at the forward direction, right? Like we know, like a beginning initial distribution, we have 2n. If we know the number of one aisles, we know the other, right? It's the only degree of freedom is 1, right? So what happens in the long run? As n goes to infinity, as we keep on iterating these generations, sampling from the previous generation, creating a new generation, what happens in the long run? It's it is not actually interesting, right? It's either 0 or 2n, right? Why? Because if you are at 0, if you don't have a you don't have any big A's, that means you're stuck forever there. Remember, there's no mutation. Right? You cannot change from small a to big A. If there's no big A contained in the previous generation, then you can only sample small a's. And the same story is good for the other direction. If you only have big A's, then you're gonna stuck there forever. So in discrete Markov chain, these two are called the absorbing state, right? And the reason why the long run goes to these or stopped in the absorbing state is that the theorem is here, is that discrete Markov chain is finite and irreducible with at least one absorbing state. Then it will eventually reach an absorbing state at probability 1. Right? And if you're not familiar with it, you can look it up. It's actually not hard to see the proof. And okay, let's see. What is some other question we want to ask? Okay, now we know that in the long run, this axon will eventually reach to 0 or to 2n. Like they exit, like the analogy of exiting, meaning that they stays there forever, and there's not, like, it's not interesting to study like the later generation anymore because they're gonna be the same forever. Right? What is the exit distribution, or in the terminology used in the book, what is the fixation probability? The probability of exiting at 2n or 0 in this case. Okay, so let's define the first thing. Okay, the fixation time. This tau, this small tau, is the fixation time or stopping time or exiting time if you have studied in different terminologies. This is the minimum amount of generation we need to reach 0 or to reach 2n. The minimum of amount of a generation we need to take in order to get 0 or 2n, right? Okay, so when we're studying, okay, the probability of exiting at 2n or 0 is denoted by this notation. We're eventually calculating this probability. X tau is equals to 2n, right? With x0 equals to I, right? With an initial state. Well, what is the exit probability with respect to its initial state? So we will compute this. How do we compute this kind of thing? So first, it is very important to use, as I mentioned, the martingale property, right? The expectation stays the same across different generations, right? We're going to use this to prove the probability of exit distribution. So we know that this is very important here. This axon is bounded by a constant 2n, and that's why we can write down the following proof. I will not go over why this is important. This is actually a theorem about martingale, but I will leave it here if you feel curious about it. You can for sure find sources about why we need this bound. Okay, we know expected value of xn plus 1 is equal to expected value of xn, and we have, okay, we can compute the expected value of xn when the initial distribution, when the initial x0 is equal to I. And this is pretty simple. Like you know that you are at xn and the beginning is x0, and you can just keep iterating. It is for sure equals to xn minus 1, right? and you can do basically the same proof as the previous computation of expectation. You get is equal to x0 is equal to I. And another way to write this, we want to build this build a bridge between this expectation and probability, right? A good way to write this is that the xn with respect to x0 equals to I is equals to expected value substrate I x tau indicator x tau. I will write it down and then explain this. Okay, what does this mean? A keynote is that when we observe when n is greater than or equal to tau, meaning that n is bigger than the fixation time, what happens? No matter how n, like maybe like n is like maybe tau plus 1, tau plus 2, no matter how far n goes, it stays as x tau forever. It is either 0 or it is 2n, right? That's this property that we discussed previously. Now what happens here? So we can divide this into two cases. Either tau is smaller than or equal to n, meaning or tau is greater than n, meaning that, or another way to say n is smaller than tau. Now we can define these are two disjoint set, right? We can separate them using indicator function. That when tau is smaller than or equal to n, this n is equal to this xn becomes x tau. And then when tau is greater than n, meaning that we hasn't reached the exit yet, we still use xn, right? But we can a trick here is to take the limit as n approaches infinity on both sides. Limit. And also here. Let's analyze these limits. What happened with the first term? As n approaches infinity, we know it stays the same, right? We proved here that the expectation stays the same no matter how far you go in the direction of the generation. And what happens here? As n approaches infinity, does it have any effect on tau? Nope. When n goes to infinity, this expected value of I, this let's write it more rigorously. Limit of n approaches infinity. We know x tau and the indicator of tau smaller than or equal to n are two independent things, right? X tau is about the number of A's in generation tau, and tau itself is a generation, right? Tau is smaller than or equal to n is independent with respect to x tau, right? So and by you can this is a very you have probably studied like the expectation of indicator function when and in the case when it's independent. And when it's independent, we can separate them, right? When we're only working with the expectation of indicator function, it is equals to the probability of tau is smaller than n, right? Smaller than or equal to n, right? This is the here this is the expectation of indicator function, right? And as n approaches infinity, the probability of tau smaller than or equal to n is going to 1. Right? It is for sure, as n goes to infinity, tau is for sure going to 1. And then, what do we get? We have this itself is just expected value of x tau, conditioning on x0 equals to I. And what happens with the second equation? Right? What happens with the second equation? We do the same trick, right? As limit of n approaches infinity, expected value of I, xn, of probability tau greater than n. Right? When n is going to 0, when n is going to infinity, this entire thing, the probability of tau greater than n is going to 0, right? And this makes the entire thing goes to 0. And by this simple limit trick, we obtain we bridge xn with x tau. Here, we have expected value of xi over expected value of xi with respect to x0 equal to I equals to the expectation of xn with respect to x0 equals to I. And this is, as we have computed here, that x0 is equals to I. Now, how do we bridge the expectation with probability? Let's recall the definition of expectation. The expectation of xn with respect to I is given by 2n times probability of I. Let's use p here. X tau equals to 2n plus 0 times probability of x tau equals 0. This is by definition of expectation, right? This is how you compute it. Oh, this is x tau. And this is 2. We know this is 0, and this becomes 2n times probably I. X tau equals 2. And then it is easy to see that by bridging 2n times probability of I, the probability of x tau equals to 2n with respect to x0 equals to I is equal to I. These two are actually equal, right? And then we get probability of I, probability of x tau equals to 2n with respect to x0 equals to I is equals to I over 2n. As an approach to infinity. And this is the fixation probability distribution. And now what is the probability? And the probability of x tau equal to 0 is 1 minus x tau equals to 2n. Because it's either the exit is you either exit at 0 or you exit at 2n, so they're complementary and they are destroyed. You cannot exit at 0 and 2n at the same time, so it's 1 minus the other. So this one is actually 1 minus I2. Okay. So now we have finished the basic definition and basic properties of the Wright-Fisher model. Most simple Wright-Fisher model is only finite number of aisles, no recombination. Now we don't even have no mutation, and we're just randomly sampling from previous generation and to just make a copy of itself to become the next generation. And these are all the properties. Next time we will talk very briefly about the Wright-Fisher model with mutation rates, with mutation probability, and then hopefully we'll be able to go over heterozygosity. Thank you so much for staying until now, and please leave any comments if you feel like there are any improvements I can make, and please leave any questions if you feel like there are something that I didn't explain clearly. And looking forward to see you in our next video. Thank you.